I'm gonna close.
have this.
I'm gonna close this. We probably don't need a. Apparently, are you host?
But if we just.
Okay, you admit people, right?
Yeah.
Okay, good.
And I tried to. And they were like, wider range.
Yeah, I mean, there's a sense in which that's exactly the right thing,
It does seem.
Oh, no.
but I don't.
Is Mason alive?
No, it doesn't.
Oh, never mind. Right.
So we get started.
The first time I in my life went to a seminar that started right on time.
So we can compute.
Squeeze in next pair.
Oh, this makes some. Oh, he's on Zoom.
Oh, really?
Alright. Should we start? 101. Okay, well, let me introduce Roger Mong, and he's he's at University of Pittsburgh right now. And he's a faculty member, and actually me and I know each other since high school. At some physics training weekend, and and then we worked together in different programs. But then he went on to do grad school at Berkeley, and then postdoc at Caltech at QAM, right? Or is it condensed matter?
I think it's condensed matter. I don't know. It's one of those.
So
I don't know who paid me.
yeah, he's gonna talk about he's gonna talk about measurement quantum cellular automata and anomalous networking. I think it's a hot topic right now and here. Okay, great.
Okay, thank you very much. It's been wonderful, and I also want to thank Lucy for the invitation and organizing my entire trip. So yes, my talk is on measurement quantum cellular automaton and anomalies in Floquet code. Practice that. Okay. Before I start, though, I do want to acknowledge my collaborators, my brilliant collaborators, Dave Asen and Jianwan, who's both at Microsoft Quantum, and Geely, a former student of mine who's now doing a postdoc at Perimeter Institute. All right, so as I first made the talk, which is actually the title of the paper on arXiv here, I realized that these are all buzzwords, and I should probably explain what it is, or any of these terms are. So I'm going to start Floquet. So Floquet typically refers to things that are periodically driven. So in the Hamiltonian, who depends on time, but there's some period t that it repeats at. And we do the standard unitary evolution of the time-varying Hamiltonian. And so we can think of that as either some periodic drive like you of some system. These are classical examples of some periodic drive where you drive the bottom and you get some inverted pendulum. And Floquet dynamics has been quite interesting, a way to generate new phases of matter and to take things out of equilibrium. It's very useful to think about the Floquet operator, which is basically time evolution under one cycle. And if you think of that as an operator, in some sense, you can think about time being discretized, in the sense that if I want to know what the state is at one particular time at units of the period, I can figure that out from the previous unit time. So one way you can think about Floquet dynamics is it takes continuous time and breaks them into discrete time. And there's a bunch of features. Specifically, we'll look at unitary non-dissipative dynamics. There could be new phases that could be realized in Floquet systems that you couldn't do with the static Hamiltonians. And importantly, it's reversible, and it's reversible in the sense that the evolution is unitary. Okay, up to some like footnotes about second law. Okay, so that explains at least Floquet. Okay, so the next thing is cellular automaton. Cellular automaton is basically a kind of a way to it can be thought of as a way to process information or a method of computing that is based on discrete time steps. So the key part of a cellular automaton is that there are classical states at every time step, and the state at the next time step depends on the state at the previous time steps and subject to spatial locality. So this is an example of a cellular automaton in one dimension, where each state, each square denoting either 1 or 0 depends on the state before that and the neighboring states in the time step before. So like this is a particular rule. So for example, if we start all zeros and a 1 here, then each time step depends on the rule before that. And because it depends on spatially local state of the system that's kind of spatially local, you kind of get these light cones. All right. This is a famous two-dimensional version of a cellular automaton called Conway's game of life, where each square, 1 or 0, depends on the square next to it. And this is one of the things where this is called glider gun, where you can kind of shoot things. And I believe both of these are examples that are Turing complete. So, okay, so that's classical cellular automaton. So what's quantum cellular automaton? Well, it's a quantum generalization of that idea, where you have a state and in the immediate time step afterwards, it depends on the state previously. And the way it's formulated is that it's a locality preserving unitary transformation. And so operators in the Heisenberg picture transforms as such, either U or U inverse one of these places. And the important part is that it's locality preserving, which means it maps local operators to local operators. So if this is an operator that sits on one site, this needs to be an operator that sits in the nearby region. So formally, it says that the support of U O U inverse is in the neighborhood of the support of O. And because of this, it also exhibits dynamics that have some strict light cone. Each time step, it can only grow, operators can only grow by a certain amount. And so this is the quantum version. And cellular automaton is kind of natural ways of describing discrete time evolution of what happens from one step to the next step.
Roger?
Yes.
I can make most of the dynamics I think about look like this by trotterizing.
Yeah.
So what more should I have in mind?
When you say trotterizing,
I take a local Hamiltonian, even odd, right?
oh, okay. So you actually hit a very important example right here. And also a very important point that's going to be a point of this talk in a bit later, about 20 minutes from now. Okay, so examples of quantum cellular automaton is basically a finite depth quantum circuit, unitary circuit, where each of these blocks represents some like short range unitary, and then you can kind of build them up like brick layers. And another example I call it quantum shift register. Some people call it like a quantum walk. Is where you take every site or every operator on support on a site and you just move it to the next site. Right. So these are going to be two key examples of quantum cellular automaton. Right. Okay.
So
yes.
So do you not necessarily they preserve in the exact spirit of how in an ordinary cellular automaton, when you're updating, you update site 2 depending on the state of site 1, but you also update the state of site 1 depending on the state of site 2, except in the quantum case you can't do that simultaneously because of no copying principle.
Yep.
Okay, so you're thinking of something more general.
Well, it could be more general or more restrictive, depending on how you think about it. The important part is that it's reversible. The classical cellular automaton doesn't have to be reversible. So that's already one important distinction. That's probably one of the most important distinction that we have. It has to, in some sense, be a unitary map, so you can't clone. So yeah, so there are overlaps in the sense that, again, there's some light cone where information there's a speed of light that information can propagate at, but the rules are different enough that a number of new features shows up in the quantum version.
But I mean, one feature of cellular automata usually is that it's the same update rule at every site and at every time. And I thought normally people for quantum cellular automata did the same thing. Are you generalizing that, or that's also?
I don't necessarily require translation invariance. Is that way? I do have time translation invariant, but I don't quite require spatial translation invariant for what I'm going to do, because I'll look at boundaries at one point.
Right.
Okay. So at least that kind of gives you the idea of what quantum cellular automaton is. It's basically some discretized formalism that you can, it's some formalism that you can describe discrete time evolution, basically, of how operators or states evolve. So then the next thing is measurement, quantum measurement. And so when I'm interested in Floquet measurement dynamics, I'm thinking about periodic, not just gates, but measurements, operations. So I kind of repeatedly measure certain, do a sequence of measurements periodically. Now, one of the important things about measurements is that generically measurement extracts quantum information. That if you have start of a quantum state and you do some measurement, you end up with a classical bit. And so if we're going to want to emphasize the reversible portion of measurement, we're going to have to think about measurements that in some sense do not extract any information out of your system. And we can call them zero information measurement and we do have examples of zero information measurements. Two of the most important example is, for example, quantum teleportation, which I'll talk a little bit more about, and importantly, quantum error correction. And in particular, that kind of gets us to the idea of, well, when I say Floquet codes, what do I mean Floquet codes? Well, Floquet codes I'm talking about in context of quantum error correction, where we're trying to use a measurement as a way to detect errors. So in the standard quantum error correction code kind of setup, you use these syndrome measurements to detect possible errors. And what you're trying to do is you're only trying to extract the errors and not the actual logical information that you're trying to store. At least that's the goal of quantum error correction. And most quantum error correction involves some periodic sequence of operations. Examples, of course, is the stabilizer code, which is basically you measure the same thing every time step. So the period is like 1. There are various like subsystem gauge codes. And then recently what been coined Floquet codes, where you make sequence of measurements multiple steps periodically. In particular, one of the most famous example of a stabilizer code is the toric code, which basically is at least originally framed. It is a square lattice where there's a side on each length. There are these 4 body measurements, which are either 4 x's or 4 z's. And this is a stabilizer code in the sense that all the terms commute with each other. So it doesn't really matter which order you measure them, or theoretically, you can just measure all of them simultaneously. And the toric code is so named because you put it on the torus, or Katai puts it on the torus, and encodes 2 logical qubits. Now, experimentally, toruses aren't the best geometry to work with, so people have also put them on boundaries. This is just one particular example of toric on a boundary. The lattice is kind of rotated 45 degrees in the previous picture, but these are full boundaries, and the logical operators now are given by red and blue. And this leads to one of the most important questions, I think, about quantum error correction, which is, if you put the toric code on something that's not a torus, is it still the toric code? All right, so I'm not going to answer this question today. recently, there's been a lot of excitement about the new code, which is kind of sometimes called the Hastings-Haah honeycomb Floquet code, or depending on some words in some order. And the way it works is that you're on a honeycomb lattice, and where now there's a qubit on every corner, every side of the honeycomb lattice, and there is a period-free schedule of measurement. So in one step, which I call R, what you do is you take all the red bonds that's labeled in this diagram and you measure qubit XX on them. So, and then the next step, which is the G step, you measure all the YYs on every pair. And then on the B step, you measure all the ZZs, and you kind of repeat. So this is a period-free measurement circuit. This is distinct from the previous case in the sense that these measurements don't commute between different steps. So you can measure all the XX simultaneously because they all commute, but the next steps, they don't quite commute with the previous one. And so this is quite exciting because it only involves two-body measurements, and depending on the architecture you have available, this might be something that you can do quickly as opposed to the full-body measurements in the previous slide. Yes.
What's the significance of the Floquet label of the letters?
For the purpose of this talk, nothing. Until at least maybe at one point I'll get to it.
Yeah.
Right now, nothing. It's from a paper that I forgot to rub out all the labels.
Sure.
Okay. Importantly, okay, so this divides all the bonds into 3 sets. This is sometimes called the Kekulé order, which is importantly different from what I guess some people call the Kataev ordering, which is when Kataev first wrote his honeycomb lattice model, the bonds are labeled by orientation. And so it's actually very important that the Kekulé order is used, otherwise bad things happens. The code doesn't work if you do say, if you divide in terms of the orientation, like Kataev did with his honeycomb Hamiltonian. Okay, so, well, okay, so again, on the torus, this implements, I believe, pretty sure 1 qubit on the torus. 2 qubits on the torus, sorry, 2 qubits on the torus, thank you. All right, so, these are supposed to be arrows. So what happens if you try to put on the boundary again, right? So this is, for example, a proposed scheme where you can put on a boundary. So in the bulk, we basically do these red, green, and blue, like these 3 steps. On the boundary, there's something that you do on it. And so Ville, I keep rubbing into the microphone, sorry. So Ville kind of proposed this particular boundaries and this 3-step cycle. Well, as it turns out, this isn't fault tolerant. And I can explain why a little bit later. So it doesn't quite work, at least for the purposes of quantum error correction code. Haah and Hastings wrote a follow-up paper where they implement a boundary, and this is a parallelogram. And the way they implement it is that you do the 3 steps in the bulk, and then what you do is you reverse the 3 steps. And so if the steps are labeled R, G, and B, the cycle you do is R, G, B, and then R, B, G, and then you repeat. So what they end up with is they end up with a 6-step circuit that they implement in order to kind of get certain desired qualities for the boundaries and the error correction code. And of course, why 6 steps? Why couldn't this be done in 3 steps? And that leads us, this kind of these kind of examples of boundaries kind of lead us to the idea of anomalies. All right, so a quantum anomaly in kind of the more classical sense is basically if you have a theory in some space that you can't quite regularize properly, that you can't put on a lattice. And we now, one interpretation is that it appears on the boundary of some higher dimensional theory that happens to be topological. And so we say the theory on the boundary is anomalous. And we have plenty of examples of this, such a number of topological phases emit interesting boundaries. For example, topological insulators or chiral phases like some of the quantum Hall examples. And the punchline of all the things that we're trying to put together is that what we're saying is we find this an anomaly in the dynamics of the quantum information at the boundary of the Hastings-Haah code. And in general, there's a classification of boundary anomalies for Floquet codes. Specifically, the main result for this paper is that there is a topological classification for, I should say, local Floquet measurement circuits. For Floquet measurement circuits, and the Hastings-Haah is just an example of that, which is in the topologically non-trivial class. And as a result, any boundaries that you try to implement is going to have an anomaly in it and cannot be gapped. And here, gapped for a Floquet code means that the absence of boundary logical operators or local small boundary logical operators. And then there's an asterisk for certain conditions that I'll have to describe a bit more later about what those conditions are. And so this is basically the 20-minute version of my talk. Okay, so that kind of explains all the technical term of the title.
Is this a quantum anomaly the same as the one people talk about in my high energy, or is it different?
Well, there's certainly overlapping features. Usually high energy anomalies are kind of anomalies of like a field theory,
Yes.
Unable to regularize it. And so in that sense, there's an overlap there that what we're going to talk about is we're going to talk about an anomalous one-dimensional dynamics that you can't quite regularize, as in you can't put on the lattice, but you can put on the boundary of higher dimensional. So in that sense, it is the same. Now here I'm talking about specifically dynamics, which I guess I don't know enough high energy to be like saying like whether they do stuff like this, but there are a lot of overlapping ideas. Now we're not going to calculate any diagrams. Yes.
So I'm not very familiar with anomalies, but so like you said that it's the boundary that has anomalous, right? The boundary theory is anomalous, but it's already boundary of something. Why wouldn't that be regularized? It's already, but it's not the right.
We have to regularize it by putting on the boundary of something
else
on the bulk.
in the bulk. Yeah.
So you can't just strip away the bulk and leave the boundary as
But doesn't it appear already as with the next to bulk right now?
yeah. So it can still appear as a theory. It's just that it always has to appear as the boundary of something.
Plus independent theory.
Yeah.
Okay.
The subsystem code version of the honeycomb model, the products of the measurement operators from the stabilizers here.
What you mean, this one?
Yeah, so here you're using a calculated structure. So are there any stabilizers in other flux operators?
Yeah. The flux operators are all global stabilizers of all these three steps, which at least is important for the analysis of this problem. It's not, I would say, the most crucial part of this code, because there's a variant of this code that has no subsystem. It's almost identical and has no subsystem things. So that's what these letters are. These represent placket stabilizers that globally stabilizes the whole thing. So the subsystem portion isn't going to be the important part of why this has anomaly.
But the product of the two measurements on the placket are stabilizers.
Yes. One feature is that like the product of, so like in the red step, you have x. That happens to be commutes with every step.
I think 6-step thing, which kind of puts the x, y, and z on different footings. I mean, a priori looking at this, right?
Yeah.
X3 and Z2.
Yeah.
Skip like,
I mean, the punchline, this isn't actually like,
but
we got a better version of this,
okay.
but yeah.
Okay. I see. Okay, but this doesn't put them on different footing, even as high Hastings did it, because they're supposed to be on the same footing, right?
The original formulation has like the three steps. There is a certain symmetry between the three steps, and this particular boundary definitely breaks it.
Okay.
That symmetry isn't, I think, that important as far as like we know. This is just one of many possible edge implementation. Okay, so. Right, so this is basically the summary of my talk. Okay, so now I'm going to try to give the same talk again, more technical detail in the remaining time. Okay, so back to Floquet measurement dynamics. So one of the things we mentioned is that we require zero information measurements. We want measurements that extract no information. And one of the prime examples is actually quantum teleportation. So to remind everyone how quantum teleportation works, at least I guess this style is that Alice has a state psi, and Alice and Bob stays a bell state. And basically what Alice does is between the two qubits that she has, she measures these two in the Bell basis. And as a result of measuring the Bell basis, you get two classical bits out. She sends these classical bits to Bob, and Bob use these classical bits to do some unitary operation. And as a result, Bob now has the original state psi. So this is kind of the quantum teleportation. And one of the important key feature of the quantum teleportation is it requires a measurement step right here. But even though there's a measurement step, Bob at no point does the quantum information get destroyed. In particular, one of the reasons why you can think about why this works is because when Alice does her Bell measurements, she will get 25% probability for the full Bell states outcome, regardless of what psi is. And so she does not extract any quantum information, any information about psi as a result of her measurement. And so this is an example of a zero information measurement, which allows the quantum information to be preserved if you think about this as a measurement circuit. Okay, so we can analyze it from the perspective of stabilizers, the same circuit. The Bell state that we're using is a stabilizer of both the XX and ZZ, also YY. We'll use XX and ZZ. And so we can think of the initial state as the some quantum information in the first qubit, and the second and the third qubit are stabilized by XX and ZZ. That means they're eigenstates of XX and ZZ. That's what I meant by stabilized. And then Alice does measurements in the Bell basis for the first two qubits, and as a result, the state is now stabilized by XX and ZZ on the first two qubits as opposed to the second. In the language of stabilizers, logical operators are basically operators which commutes with all the stabilizers. And logical operators, applying logical operators, how you think about manipulating the quantum information encoded in the stabilizer code. So in this particular example, the logical operators in the very beginning, I'll do an example, is X11. So one way I can manipulate the quantum information at the very beginning is by applying an X operation on, this is where psi used to be. And you can see that commutes with the stabilizer code at the very first step, one XX and one ZZ. There's an equivalence of logical operators is that I can multiply by any stabilizer, and it's still the same logical operator, or equivalent logical operator. So in particular, X11 is the same as XXX, because if I already know that my state is an eigenstate of 1XX, then any operator, if you multiply by that, is an equivalent operator. The reason why XXX is particularly convenient is that XXX is also a logical operator of the next step, whereas X is no longer a logical operator of the second step because it doesn't commute with the ZZ1. And XXX is equivalent in the second step as 11X, because in the second step, we've measured the first two qubits, so it's become stabilized by XX1. And as a result, you can see the logical operator X on the first qubit transforms to the logical operator X on the third qubit. So this is one way we can analyze the quantum teleportation scheme in the context of logical operators. And the same thing applies to Y and Z on the first qubit. It teleports to Y and Z on the third qubit.
So Roger, is the important result that I have two codes on the same physical qubit with compatible logical, like I can pick the same logical operator and use it for both codes?
Yes, it's important that this step can be done. And
so like really I should be thinking about this XXX operator.
Yes.
And the other,
yes.
Yeah.
And that's actually a great point. I'm going to talk a little bit more about that. We give 6 equivalent criteria for when you can tell that these two are compatible in the sense that I can go from one to the other with no loss of quantum information. And one of the 6 criteria is that there's a common set of logical operators such as XXX between them.
This is like what stabilizer groups have the same normalizer.
It's in the paper.
Okay.
And is in the paper, and I probably won't go that deep into like the equivalent conditions. I'll kind of give a more heuristic of what's happening. All right, so the way that we want to think about this is an example of a circuit dynamics. Where you can imagine, well, these are the set of measurement operators I have. These are now the set of measurement operators I have. And the formalism that we actually use is what's called the instantaneous stabilizer group, which is basically the stabilizer group at that moment. Specifically, it is the set of Pauli operators that has eigenvalue +1. And what happens is every time you make a measurement, you can think about the measurement updates the instantaneous stabilizer group. And so, for example, if I make a measurement M to update ISG, which is a group of Pauli operators, then the new stabilizer group is going to contain M because you've just made a measurement plus or minus M because you've just made a measurement of M, but it will almost retain all the previous operator that commutes with M. So if I measure X at one point and then later I measure a different, say something that commutes with, say like XX, then the first measurement stays in the stabilizer group.
What's the relationship between reversible measurement circuits and zero information measurements?
In terms of the equivalent, or that's the formal definition for us that we're using for a Pauli zero information circuit is that it is reversible. And this is kind of condition. Okay, so mathematically, the way that we write this is that the new instantaneous stabilizer group contains M, and it also contains everything that commutes with M, this is notation for everything that commutes with M. We say it's reversible, basically, if you can find a different measurement or the same, M prime, that goes from the new ISG back to the previous ISG. So that's one equivalent definition for reversible. And that kind of tells you that you haven't took any information out. And there's one way you can think about, a practical way you can think about whether a particular measurement is reversible is that every measurement that you make between instantaneous stabilizer group either has to satisfy one of these 2 criteria. It either commutes with everything that's already in your stabilizer group, which means that you're measuring something that you already know for certain what the eigenvalue is going to be. So that's one way you make sure you never extract any information. So repeating a measurement is an example of something that's in this class, or it has to anti-commute with at least one element of your instantaneous stabilizer group. And that guarantees that you always get 50-50% probability outcome of that measurement. What you do not want is to measure something that commutes with the ISG, but it's not in your ISG. And that's because that's a logical operator. That's a non-trivial logical operator. And that is the step that extracts quantum information. So as long as you kind of stay within the first 2 class of measurements, that is another way to frame how it's going to be reversible. Okay. Oh, any questions? Yeah.
So in the previous example you gave us for teleportation, is that like the X1? The X11 is splits that like when new measurement splits.
Okay, so this is the first instantaneous. These 2 generates the instantaneous stabilizer group at the first step. These are the kind of measurement you do at the second step. What the XX1 does is that it does not anti-commute with this one. So as a result, if I were to measure this one, it will replace this one.
Right.
And so you're still good. And then ZZ1 anti-commutes with this one. And so these are why both of these are forms reversible. And here you can explicitly see it's reversible because there's a symmetry between the first and third qubit. You can basically reverse the teleportation back to Alice by basically measuring these again. So here explicitly you can see it's reversible. M perpendicular is a set of Pauli operators that commutes with M. And so this says that everything in ISG that commutes with M, that's what this term is notation for.
first line when you say Pauli operator with eigenvalue, it's not a maximal set of Pauli.
It is, well, it's not,
It won't uniquely specify.
this does uniquely specify all the ISG, this criteria, I believe.
No, it doesn't uniquely specify a state.
It does not unify a state.
So if the Kitab, we take the Kitab or sorry for model, the non-local, the non-trivial loops are not included.
Yes, that's correct. Yep. Yeah. Yeah, so this will restrict your Hilbert space, and the point of quantum error correction is that you still have some finite Hilbert space left. Okay, so what we want to talk about now is we want to characterize quantum dynamics. We want to, in particular, want some of the characterization is the flow of information, and there's also various topological characterization, right? Like what dynamics can or cannot be deformed to another one. And we've mentioned previously, when we're dealing with unitary dynamics, the formalism is called quantum cellular automaton. And so in our work, basically we extend this for measurement dynamics. We extend this concept to what we call the measurement quantum cellular automaton as a formalism to describe the dynamics. I'll describe a bit about what QCA is. So again, QCA is more technically now a locality preserving automorphism of C-star algebra. And we can even do a bit better of a product C-star algebra, which basically is a way of saying that it maps operators to operators such that the operator algebra gets preserved. And so, you know, UOU dagger preserves both addition and multiplication of operators. And again, these are kind of the two standard examples. This is kind of the trawlerized quantum circuit, or what we call finite depth unitary circuit. And this is a quantum shift register.
Why does the circuit have to be finite depth?
Well, okay, so a QCA requires operators to transform to an operator that has supported in some finite neighborhood of the original operator. So there's a strict kind of distance that operators goes at. And so having a finite depth guarantees that's true, that you get a QCA. Now, you might be very clever and find a way to implement a QCA using a non-finite depth unitary. But these are, I should say, examples.
The notion of the honeycomb and restricting how much an operator grows for one time step, that's a characteristic of one time step, right?
Mm-hmm.
Whereas finite depth is a characteristic of the length of the entire circuit, right?
Okay. Sorry, can you ask that question again?
Is it finite depth is a characteristic of the entire circuit?
Yes.
So I'm wondering how this characteristic of one time step, why that should restrict the length of the entire circuit.
I think the confusion is that you're using this finite depth circuit as one time step of the cellular automaton, is that right?
Yes.
Okay, thank you.
Oh, yeah. Okay, so yeah, so this is one time step, and at least in this particular example, I believe that the light cone goes at most either 6 or 7 sites, bigger than your original size because it's of the depth of the circuit. This one you can see that because you're shifting all the operator by one, your operator support is always going to be one bigger at most. Now, this gets to a question that Chris asked earlier. So these are both examples. There's an important result from these 4 authors, which I will abbreviate as GMVW, and basically, which measures the flow of quantum information, which is left versus right. And in this one, you can kind of see that in this shift register, everything kind of moves over to the right by 1. So any operator starts here, moves over to the right or 1, or any state kind of moves to the 1. Here, it turns out there's no net flow of quantum information. Any information that moves to the right is compensated by some other information that moves to the left. And visually, you can imagine, well, is it possible for me to implement this circuit using, say, a bunch of swap operators, right? And what happens is, well, I can say do a swap operator between these two, which moves this one to the right one, but this ends up moving to the left one, right? So with a finite depth of swaps operators, for example, I can't globally move all the information over to the right. And this idea is specifically captured by what's known as the GMVW invariant, which measures the flow of quantum information, where this has index 1 and index 0. And so one important result is that any finite depth unitary circuit or any unitary evolution from a local Hamiltonian can never have a non-zero index, that you have a class of QCAs that cannot be implemented by a finite depth or shallow depth or local Hamiltonian dynamics. All right, so is there ever a way to kind of do this? And the basic answer is yes, but only on the boundary of a two-dimensional circuit. So this is an example of a circuit by Hopper et al., where basically they have a box square lattice and they do certain swap operations in 4 steps. So these highlight swap operations, and basically it's done in a way so that all the quantum information in the bulk goes around in a square after 1 step, but on the edge, it moves by 2 unit cell on the boundary, depending on which boundary you're on. These are all swap operators, so you can kind of just manually work out what happens to every qubit after 1 full cycle. And you can tell this is an example where on the boundary, you now have net motion of quantum information that's compensated on the other boundary. But this is only possible because we're doing it's on the boundary of a circuit in 1 higher dimension. And so this gets us to basically the idea of anomaly, which says that one-dimensional dynamic. We have examples of some one-dimensional dynamics that can only be realized at the boundary of a 2D circuit. And one way to characterize that is you can ask, what's all the possible unitary dynamics modulo what's the stuff that you can implement in 1D, finite depth unitary circuit, and it happens, at least for cubic Clifford gates, you get an integer, which characterizes the how many qubits gets transport along the edge. And so the question I have in the remaining is an hour long, right? In the remaining less than 50 minutes is what are the analogous ideas for measurements? Okay, so probably I'll try to go quickly. Okay, so what I have here is a table of the ideas for unitary circuits and analogous idea for measurement circuits, which is kind of, this is the crux of our work. And so in the unitary circuit, we're required to be unitary, which is importantly invertible. And the analogous idea in the measurement language is that what we call zero information measurements, or what we call reversible measurements. The analogous idea of a finite depth unitary circuit, which you can think about as being built up by a local unitary, is what we call a locally reversible measurement circuit. And I don't really have time to define what locally reversible means, but the short answer is means that quantum information only propagates a finite distance after each circuit step. The generalization of what's called quantum cellular automaton is what we call measurement quantum cellular automaton, where we basically track the flow of logical operators. And then we also define an index analogous to a GMVW invariant, which we call the MQC index. Very briefly, a locally reversible measurement circuit is a sequence of reversible measurements. The M's are the measurements, and the A's are the instantaneous stabilizer groups that returns you to the same stabilizer group after 1 cycle. So you basically keep updating the stabilizer group after every measurement, and you have to get the same stabilizer group at the end. A measurement quantum cellular automaton, what it does is that it tracks how logical operators transform. Specifically, we require an analogous to QCA that logical operators maps to nearby logical operators. There's a way more technical version of that statement, which if you're interested, I can tell you how it's actually defined. But basically, we're tracking the flow of logical operators. And the MQC index basically measures that flow in analogous to how the GMVW index measures the flow of quantum information. Okay, and the main result that we have is, okay, so the fonts are all wrong. This is a subset symbol. This is a subset eco symbol. This is a subset symbol. All right. So the first two we've already talked about. We already mentioned how one-dimensional in 1D, one-dimensional quantum cellular automaton can cover more cases than finite depth unitary. So this is why this is supposed to be a subset symbol. And the difference, at least for Cubist and Clifford, is integers. What we find out is that locally reversible measurement circuits can actually implement all of QCA. So that measurement circuits already is more powerful than finite depth unitary circuits in what they can do. So this is an eco, or eco with a squiggly on top. And then this is a subset in the sense that we also found out that there's certain measurement dynamics that can only show up at the boundary of a 2D system. And this difference happens to be a Z2. So there's basically a Z2 classification of bulk measurement circuits. So this is kind of the more technical results. All right, so very quickly, the way that you do translation by measurement, so we said you couldn't do it by unitaries, because every time you send information to the right, some other information goes back to the left, because quantum mechanics kind of works in this way. But it turns out if you allow measurement, this is an example of a circuit that translates all the information by one, and it basically uses the teleportation scheme earlier repeatedly. And so the way it sets up is that here's all the qubits, logical qubits. There are all these ancillas that you need. And what you do is, in the first half step, you teleport every qubit to the next ancilla, and then in the next step, you teleport the ancilla to the next qubit. And as a result, we can get a net flow of quantum information in one direction. And so this is what this is an example circuit that has MQCA index 1. This is another example that does the same thing. All right, so to kind of explain why there is a boundary anomaly is that we are able to construct a circuit with MQCA index 1/2, which and so the way it works is this way. Okay, so if I kind of, oh crap. Wait, press the wrong button. Okay, so if you one way you can analyze the circuit is to ask what happens to the logical operators. In particular, the logical operators of this circuits are basically operators that manipulate the logical qubits. So there's a Pauli X and a Pauli Z on every side. These generate the full algebra. And so the logical X here becomes the logical X here. The logical Z here becomes the logical Z here. So that's one way you can think about what the circuit does to the logical algebra. This is a setup where, okay, so importantly, there are two Pauli generators. There's two generators to the Pauli group, I should say, per site. In this example, which I'm going to explain very briefly, there's only one Pauli generator per unit cell. So, and the way that we do this is that we take the Graham-Plackett's model or the toric code, and we basically use one of the boundaries where there's not only one logical operator per unit cell. So this is a particular implementation where these are the stabilizers in the bulk and on the edge, and the logical operators on the edge are basically these two-site operators that lives here. And if you implement a translational circuit on top of this, what that does is that it takes these logical operators on the boundaries and moves them to the next site, just as expected. But because there's only one logical operator per unit cell, logical generator, that the MQCA index, the measure of flow of information, is 1/2 in comparison to the teleportation circuit that I showed earlier. And this is kind of the idea of basically how we can get 1/2 is as opposed to an integer, and that's the origin of the Z2 index. And this is kind of a more precise kind of set of stabilizers that does exactly what I just said. Yes.
So is the point here actually the ancilla that makes you possible to move the qubit and not really the measurement? Because like if I imagine that I have an additional set of ancilla and I do the swap gate, I can also do the qubit shifting using only like unitary.
Yes. So there's an equivalent circuit where you do a bunch of oscillators. You do the swap gate, so all the ancilla goes to the left and all the logical one goes to the right, and then you measure the ancilla, so you don't call them, like you start having them measure and you measure afterwards. That is an equivalent circuit, and you can think about that's kind of one reason why we circumvented the GMVW theorem.
So in that case, it's the measurement of the ancilla after you do the swap.
That's one. Well, so in this particular circuit, that's not why, but like that's one way, like in the swap measurement circuit, you can think about that's one reason why you only have quantum information going this way. It's because all the ancilla goes in the other way, gets measured out.
Yeah, okay.
That's kind of one way to think about it. Okay, so before I finish, I'll kind of give a TQFT picture of what's going on. The TQFT picture is that, okay, so in the previous example, the Wern-Plackets model, and also in the Hastings-Haah model, what happens is after every cycle, the E anion gets transformed to the M anion. So one of the features of the Wern-Plackets model is that each placket, quote unquote, possibly traps an anion, but it's like a checkerboard pattern where it's like alternating E and M. So by doing a translation by one unit cell, I basically change all the E's to all the M's and vice versa. So if I think about some bulk circuit that basically changes E and M after one cycle, after some number of steps, where I change this E and M, okay, so now you look at the boundary, right? So suppose your boundary, in this TQFT picture, what I have is I have like a M condensate, E condensate, M condensate, E condensate. And between every condensate, you can think about it as trapping a Majorana. The other way you can think about it is that logical operator. So this is the toric code, this is the vacuum. I apologize for the poor resolution. Logical operators are generated by strings that goes between the condensate of the same kind. So this is E to E, M to M, right? So there's another E to E here, but that's the product of this times this. So the pattern of condensate is determined by your stabilizer group, which is determined by kind of the measurement. So after every cycle, you have this pattern of condensate. But the logical operators, the dynamics are dictated by this automorphism that switches E and M. So after one cycle, this E can't possibly stay still because the E becomes an M and I can't have an M string between two E condensate. So one solution is that all these logical operators shifts over from blue to red, which in this picture is half a unit cell. But what that basically does is that you're basically taking an operator and you're shifting over by one. And so the TQFT index basically, the TQFT picture basically has to do with this non-trivial automorphism. And what happens is if you run 2 cycles of this, you're fine because at that point the anions gets restored, the anion labels gets restored, and so there your MQCA index is an integer again, which is something that you could do in one dimension. So this is kind of the picture about why. All right, so all right, so to do it algebraically, basically we have an MQCA index, which basically measures the flow of logical operators, and it's always a multiple of a half in 1D. And one of the theorems that we prove is that in any one-dimensional locally reversible measurement circuit, any circuit implement 1D, that index has to be an integer. And so if you get a non-integer, that means it has to be at the boundary of a 2-dimensional circuit. And this quotient is Z2, so this is Z2 anomaly for these circuits. And importantly, so if you ask what a gap boundary is, a gap boundary in the language of Floquet codes is where we don't have small logical operators at the edge. And for that to happen, you have to have index 0, because if there's no small logical operator and you ask what's the flow of logical operator, well, there isn't any. And so whenever you get any 2D circuit where the boundary is not an integer, that means you can't gap it out. You must have logical operators on the edge.
You said in this case, gap boundary means there are no small operators on the boundary.
Yes.
Why should I think of that as a gap?
Well, logical operators in some sense, I guess, are analogous to degrees of freedom in kind of the more unitary case. And so it's basically saying that you don't have any kind of local degrees of unitary degrees of freedom. Long logical operators in some sense are typically associated with topological, like kind of like degrees of freedom, like maybe like defects or like or pin anyons. And so so those are, I guess, we think of them as it's still possible to have them, right? Like when we think about like a gap state, you know, we still allow, say, topological kind of degeneracies, but we don't allow local degeneracies. That's kind of the analogy of why I call it gap. That's also why we put in quotes, but it's just the analogy from a Floquet measurement setting to a unitary setting.
Yeah, maybe follow up to this question. Is it terminology kind of suggests some kind of robustness of those local degrees of freedom? Like if you ever perturb the circuit away from the designated like trajectories, like does that follow through, or is
There's a certain robustness in the sense that if I have a measurement circuit that has a particular range, I'm going to need at least one logical operator per, if the range is R, I'm going to need one logical operator per R unit cell at least, because I need a bunch of logical operators to kind of move on the boundary, and I need to have enough of them so that one can go into the next one. So in that sense, there's kind of a robustness. You can always dress it up by adding more logical operators.
and just to be clear, this is all kind of within this framework of only considering stabilizer, like
Yes. Okay, so it also turns out the Hastings-Haah code, because it's an E&M automorphism, also has this feature, and that's the reason why after every 3 steps, you can't find a trivial boundary. And so one of the things we basically prove is that one of these 3 things has to happen. Either you period double it, that's the simple way. You either break local reversibility, which is the idea that you allow logical operators to jump a long distance in your circuit. This turns out to be not very good for a quantum error correction, because at least in the examples that we know, the string operators, the big string operators loses topological protection if you try doing that. Another way is that you have an anomalous boundary. But what this is that means you have a large number of logical operators, a thermodynamically large number of small logical operators, and that typically is also bad for quantum error correction. So what our theorem basically says is that the most preferred way to run a code like this is to period double it. All right, so anyway, this is kind of the summary and the concept and the application of what our work is, quantum error correction. I'd like to thank my collaborators again, and I'd like to thank for your time.
Can you go back one? I'm trying to understand the connection between breaking local reversibility and getting, I guess, getting logical operators. Is it that like an error spreads via this failure of local reversibility?
Okay, so I never define what local reversibility is, but basically it guarantees that logical operators goes to logical operators that's nearby. An example of something that's not locally reversible is this that giant X that I had 50 slides ago, this one.
Yeah.
And what happens is, for example, whoops, I believe there's like a logical operator that goes from, I don't quite remember, here to here, and the next step it goes from here to here. So like, if this was like the system size, it moves a very big distance. What happens, at least my understanding, is that when that happens, you have to do steps to update your logical operators, because your logical operators needs to be transformed by the results of the measurement. Just like in the quantum teleportation, the results of the measurements are very important in making sure your quantum information actually gets preserved. And I kind of swept that under the rug. And what happens if they move a long distance is that they require a large number of measurement sequence all to be correct for you to be able to figure what the next how the logical operator gets updated. And so I believe what happens is that when you break the local reversibility constraint, you now run into problems in terms of measurement errors can basically cause loss of information.
You have like an extensive number of measurements.
Yes.
That all have to be right. Yeah.
Yes.
So can I think of these measurement quantum cellular automata like as a generalization of quantum cellular automata, which are like automorphisms of the local algebra?
Yep.
Somehow measurement quantum cellular automata are like an automorphism of a subset of the local algebra.
Very close. So the measurement quantum cellular automata is the automorphism of cosets of the logical algebra modulo the stabilizer group. So the cosets is the logical algebra modulo the stabilizer group. And then there's an additional locality constraint that I can tell you later.
Okay. And then what is the distinction to what I said? Where
You said subset.
Yes,
I said
I'm asking like what is the way in which what I propose differs from the way in which.
Well, when we think about logical operators or logical algebras,
Yeah.
so there's an equivalence between logical operators because you can always multiply them by a stabilizer. So I think the formal way to think of them is cosets.
I see. So you're just saying
The
it's-
logical quotient, the stabilizer.
So rather than the subset, the quotient.
Yeah.
Okay.
Not sure if I missed it, like, is the MQCA index something that you can directly measure in some kind of observable circuit? Like, especially when you get.
You can
like,
definitely compute it classically, knowing what the circuit is.
Like, the question is, like, suppose if you actually realize that, is that something like you can directly measure in any kind of observable that is local?
Well, I mean, so for example, suppose that, like you can ask, well, like in quantum teleportation, well, okay, no, wrong direction. In quantum teleportation, like how do you know it's work? Well, there's certainly correlation experiments you can do to verify this works, right? So then I would guess that if someone was trying to implement, say, this particular circuit, there's some equivalent correlation or tomography that you can do to verify that, oh, this is working. So I would imagine probably.
Sorry, I just want to make sure, because the MQCA index is a Z classification or zero classification.
It's half of an integer classification,
Half of
so
it.
Z/2.
Okay, so if half of an integer, can I take some negative values and something like that?
Yes.
Okay, so in that case, if I have one layer with the positive one, the other layer with the negative one, and I couple them together, will some of the anomaly you mentioned disappear in the sense?
Yes.
Okay.
But even one is not anomalous because we know how to make a one-dimensional circuit with integer index. So it's only half that's anomalous.
But one is anomalous if it's not in the MQCA.
In the QCA, one is anomalous, yes. I don't know when this ends.
Alright.
Thank you.
Somebody does not.